guess I forgot to start recording. It doesn't make a lot of sense to talk about how fast something is going if we don't know what direction it's going in. The directions that you wrote on your note cards over the last couple days had a magnitude and a direction. 4 meters north, 3 meters south, 2 meters west, 56 meters east. Those are vector quantities. If you just wrote 4 meters, it doesn't tell you what direction to go in. It can be any point of the compass. You can spin in a circle. That said, a lot of what we're going to do in this chapter is going to involve tracking vectors. So the maps that you made yesterday were a way of tracking vectors. When you're tracking vectors, and this is, visual learners love this part, there are all kinds of pictures. You've got to draw a picture to make sense of the physical vectors. So if we have 10 meters to the right, and then we go back 5 meters to the left, we can figure our displacement. By looking at the picture, we can very easily determine our displacement. What's our displacement here? 5 meters to the right. And again, we have to have both a magnitude and a direction. Some of this is common sense stuff. You can't add meters and centimeters. Just like in our earlier chapters, we talked about not adding quantities with different units. You also can't add quantities that have even, are in different scales. So you can't add velocity and displacement. Also, you can't add quantities that are measuring different things. You can't add acceleration and velocity. When you add up vectors, what you get is a resultant vector. So we're going to start with a couple simple resultant vectors. I'm going to imagine this is a map. We're going to use cardinal points of the compass a lot. So we've got north, south, east, and west, however you choose to remember that. There's never eat soggy Wheaties if you struggle with that. But our bizarre little bit of heritage from a seafaring past is that we orient with north up, so we envision the compass rose with north up. Maps were not always that way. The term orient comes from the fact that the orient used to be at the top of the map. They used to be oriented with the east up, but we do north up, and we've done it for a long time, so we'll stick with that. If I tell you that someone travels, and we'll say that each block is 1 meter, and we travel 1, 2, 3, 4, 5, 6, 7, 8 blocks, so 8 meters east, and I'm going to not superimpose these. 1, 2, 3, 4, 5, 6 meters west, and then that out of the way. 1, 2, 3 meters east. What's my resultant vector? So in truth, what I should do is have all these superimposed on one another, so I'll go ahead and do that. But I'm going to use different colors to make it possible to see them. Okay. So I've got my vectors, they're all there. My resultant vector I almost always do in red, and the resultant vector goes from the tail of the first vector to the head of the final vector. There's my resultant vector. So how far did I go? What's my displacement? 1, 2, 3, 4, 5. Could you have done 8 minus 6 plus 3 meters? Yeah, of course you could have. There will be some, obviously, you know that this all gets nothing but more complicated. So we would call this delta x resultant is 5. There are no sig figs here are terrible. So if we're doing a good job of bookkeeping with this, delta x1 equals 8 meters east. Sticking with my color coding, delta x2 equals 6 meters west. I'll move these up a little bit. And delta x3 equals 3 meters east. My resultant vector, I guess I should back that up a little bit. My resultant vector is the sum of delta x1 plus delta x2 plus delta x3. Now that's one-dimensional motion. That's all on a single axis. Does it get trickier than that? Of course it does! Okay, so now what if I continue to have this orientation, and I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So delta x1 equals 10 meters east. Well, then I'm going to throw a loop into things. 1, 2, 3, 4. So now I have some y motion. Delta y1 equals 4 meters north. And then I'm going to go 1, 2, 3, 4, 5. So delta x2 equals 5 meters west. And let's do this one in a nice green. I'm going to go 1, 2, 3, 4, 5. Delta y2 equals 5 meters north. Where's my resultant vector? Tail of the first vector to the head of the last vector. Now, can we do that with some other form? Can we do that mathematically? We can, but we're not going to yet. Okay. Or displacement. This is also a little bit like what you did in your lab yesterday, in the last couple days. You did a whole series of north, south, east, and west movements that got you some place. So now let's think about the rules for tracking vectors, or the properties of vectors. You can move a vector parallel to itself in a diagram. So if we borrow this, does it matter if I move here before or after? If I take that westward 5 meters, does it matter if I do that before or after I go north? So would I get to the same relative position? Here, I'm going to copy this again. Copy, paste. Do I get to the same place if I only go 5 meters west and then I go a straight 10 meters north? Oh, look at that. Did any groups take out their cards and subtract easts from wests? Okay. So that's an easy way to do it. Oh, well, they had us go 15 meters west, but then they had us come back 10 meters and then go back 5 meters and then go back 10 meters. And, okay, overall, we only need to go 5 meters west. Okay. You can move vectors parallel to themselves in a diagram. You change your start point, but the magnitude doesn't change, the direction doesn't change, and you can add them up in different orders. You get the same resultant. A few of you are grinning, like this is exactly what we did in the lab. So we can subtract vectors by adding opposites. And again, if we go back to this little diagram, I'm going to copy this. Whoops. No. You know, if we pay attention to this one down here, that's 5 meters. We had 10 meters east and 5 meters west. When you add 10 meters east plus 5 meters west, well, you get 5 meters east. But that's only possible if you're doing one of two things. You're using the graphical representation of the vector, or what's the other way that you could do that? There's something we used in the last section of chapter 2 as a proxy for direction. Use something as a proxy for direction. Talk at your tables. Don't yell it out. There was something you were using as a proxy for direction, and it was really important. Nice try, though. So I'll give him extra credit. Yeah. Sign is what we use as a proxy for direction. So you can't add east and west, can you? No, you can add the graphical vectors. But if you take that Cartesian coordinate system, which now as we look at it is starting to look an awful lot like a compass rose, and you say positive, negative, because we're so fond of slapping the Cartesian coordinate system on the whole planet, then suddenly this becomes 10 meters in the positive direction, and this becomes 5 meters in the negative direction. Oh, well then we have positive 5 meters east. Make sense? One of the cool things about vector properties, or vector quantities, you can multiply and divide vectors, you still have a vector. So velocity is a great example. If you double your velocity, you're now going 2vu. I don't know. It seems funny to me, but I don't know why. What? So if your initial velocity, the velocity of u, is whatever it is, and we double it, we have 2v sub u. We can do 3 times as fast, 3v, 0.5v. What we end up with is still a vector quantity. We still have to use the direction that we had. So this would have to be, 3 meters per second west, 4 meters per second up, any of those. Okay, this is the thing that we just mentioned. We tend to slap the Cartesian coordinate system on the whole world. For better or for worse, it's what we do. And that means up is positive, down is negative, like we did in chapter 2. It very often means that right is positive and left is negative. Don't confuse left and right and north, south, east, and west. In terms of coordinate systems, we do run into a few problems where the coordinate systems are weird, and you're trying to describe something in terms of, upfield, downfield, to the side, across, The other one that we sometimes use is above and below the horizon. And again, those are not the same as north, south, east, or west. Those are not the same as left and right. So we just have to be careful with the coordinate systems, and you'll get lots of practice. You will need a straight edge, or a ruler actually, and you will need, not a broken one, what do these people do? You will need a protractor. Fortunately, I have both. Go get them. I will say that it is very hard to do these problems on the DISC series. So I'm going to do my best, but then I'll probably, after I do one as sort of a walkthrough, I'll break and start doing them on the board. With the graphical solutions for resultant vectors, this rewards very careful measurement. Very careful measurement. Precision measurement. Lining things up carefully. You have to know how to scale things. And colored pencils, colored pens are really helpful. And some of my visual learners have already got a barrage of colored instruments out there. If you are not one of them and you want to grab colored pencils, I have them. So let's imagine that we have something that travels 30 meters north, turns, and travels 10 meters at, now here's where this gets all funky, at 45 degrees north of east. What? What is north of east? What is 45 degrees north of east? North of east. What? It's in between. So we're going to do some compass rose fun and games today. Reindeer games with the compass rose. So let's start off with our first vector. Now, on the first thing that you're doing on a piece of paper is you're going to choose a scale. So a really easy one for most problems is that 1 centimeter equals a meter. On mine, I'm going to assume that those little boxes are 1 meter each. If you're using graph paper, you can do something like that. Now that gets dicey when we're not on an X or Y axis. Okay, so I'm going to have a start point here, and I want to go 30. I'm going to have to use smaller graph paper, actually. Ouch, that hurts my eyes. Okay, sorry, we changed that to 15 meters. You're, of course, scaling this. I'm using the little squares. So I'm still going to start off fairly low. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, now what happens here is a little weird. It says that we travel 10 meters at 45 north of east. So at the end of my first vector, I'm going to do this bizarre thing where I'm going to stick a compass rose here. Okay. And I'm going to label it north, south, east, and west. And if I zoom in on this, what I'm going to do is I'm going to imagine starting at the east, because I'm going north of east, and I'm going to go up 45 degrees from the east toward the north. Now, my object, whatever it is, travels 10 meters at that heading. I'm kind of having to fudge this on Doceri because, of course, when I pick up my line to move it, it may very well move. I tend to write the degrees in here as a matter of good practice. So now I'm going to do my resultant vector. My resultant vector goes from the what to the what? Tail to the head. Make sure you put arrows on these things or you can't tell which is the heads and which is the tails. That is my resultant vector. So this is, now is that delta x or delta y? No, it's just my displacement. It's just my displacement because I'm no longer on the x and y axis. So this is my, sometimes we call it D resultant. Sometimes we just call it the resultant. We can call it a whole bunch of things, but that's my resultant vector. When you measure your line, so now here's your job. When you measure that line, this is all drawn very carefully to scale, right? Yes. Measure your line. And then multiply by your scale factor. So, who's right? We don't know. These are all in the same ballpark. We can pretty well say that the displacement is somewhere around 24 meters. Now, you're not done. Because if the displacement is 24 meters and it's a vector quantity, you also have to have what? Direction. So you know that protractor you got right there?
Yeah.
You're going to go down to the base of your first vector. You're going to redraw your compass rose at the base of that first vector. Mine is imperfectly drawn, please forgive me. And you're going to measure the angle. Now, you can measure this angle. You can measure this angle. They describe the same heading, but how you describe it will be different. By golly, what's the relationship? They're complementary angles. They add to 90. And it is, neither of them is incorrect. You can use either of them. So what would be our final resultant vector? We would say that our resultant was, I'm gonna say it's, because we don't have a great degree of significant figures here. So I'm gonna say 24 meters at 19 east of north. That would be our final answer. Now, we're going to do these algebraically later. Why would we use this? It's clunky, it's awkward, there's no one right answer. Dear Lord, what are you trying to do to me? I want definite answers. It's okay, this approximates what we've got. Now, you have to be all kinds of picky and precise and careful. You have to line your pencil up perfectly. You have to account for like the width of your pencil lead. If you use a slightly larger drawing, you have to do less of that. If you use a little tiny drawing, you have to do a whole lot of that. Tiny drawing people. But it's a good double check when we do these algebraically, because multi-piece travel, multi-piece displacement that is not at right angles is complex algebraically. I mean, it's not hard, it's just messy. This is a good double check on our work if you draw it out to scale. Questions, comments, concerns so far? So 1, 2, 4, and 5. The FIP on this will probably be, this is Thursday. I'd assume that we'll have a FIP about Tuesday or Wednesday of next week. Let's play compass rose games. So this is east of south. This one is south of west. Now let's do a tricky one. Here's the horizon. I have a little airplane. This is the worst airplane I've ever drawn in my whole life. The little airplane goes along the runway, and then it takes off, and its resultant vector is there. What's that angle? Sorry.
Up, down.
Above the horizon. Up of horizontal. Yes. We have no idea what direction this plane's pointing. We don't know if it's going north, south, east, or west. You didn't have a compass on this. It's a plane, for Pete's sakes. But people will do that. People will look at this and they'll go, oh, that's easy. That's north of east. No, it's not. We're talking up and down here. We're not looking at it from the top side on a compass rose. So be really careful in terms of not mixing those up. We do a bunch of plane problems like this, where we have planes that taxi down a runway and then take off at some angle and then correct what's their resultant displacement. Well, it's, so many meters at degrees above the horizon. So you'll see a few of those in the homework, I think. Okay? Questions, comments, concerns?